Hello, and welcome to part two of this podcast on basis sets. So far, what you should know is some of the basics of basis sets. For example, you should know that basis sets are a set of numbers that kickstart the calculation of the Schrodinger equation. Specifically, they kickstart the determination of the wave function called psi. In this podcast, we're going to talk a little bit about some of the more advanced basis sets, which are the ones that you are typically going to use. So this chart here is showing sort of a combination of both the basis set and a level of theory. So going down the left side of the chart, what you see here are the different types of basis sets that we're going to talk about in this particular podcast. So far, you have dealt with what's known as a minimal basis set. So an STO2G, which is, as you should know by now, a way of approximating a Slater type orbital by combining or adding two Gaussian type orbitals. And we did that lab in the session. In this podcast, we'll talk about split valence, polarized, diffuse, and a little bit about high angular momentum. And we'll also talk about contraction correlated basis sets. So going down the left-hand side there, listing the basis sets. And what you see there are some dots, which means there's an infinite number of basis sets that can be used, and one of the big areas of research in computational chemistry is trying to come up with a basis set. Okay, going across the y-axis or going from left to right, what we're showing there is a level of theory. So we have Hartree-Fock or an ab initio method. Actually, all these are ab initio methods. We have Mollier-Plesset 2, Mollier-Plesset 3, MP4s, some of the more advanced levels of theory, and then dot, 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 all the way over to what's called full CI, which is a very advanced level of theory. And what we're trying to show with this chart is that with a perfect combination of a basis set going down the chart and with a level theory, by the way, you should note that it shows electron correlation going from left to right. Hartree-Fock does not use any correlation between electrons. In other words, one electron doesn't necessarily see the other electron. So going across from left to right, we are increasing the degree to which, mathematically at least, electrons are seeing other electrons in a molecule. So if I go down all the way to the bottom and to the right, all the way to the right, I will be able to solve Schrodinger's equation exactly. And the dot, dot, dots in between the basis sets and the dot, dot, dots in between the electron correlation should suggest to you that we are a long way away from being able to solve Schrodinger's equation directly. The reason that I have the three basis sets under HF filled in here is this is the playground that you are primarily working in. Most of the time, you're going to be using a semi-empirical, or excuse me, a ab initio method like Hartree-Fock, or a density functional theory method like B3LYP. And so you'll be in that playground. Rarely are you using an advanced electron correlation method such as MP2 or MP3. Most of the time, your basis sets are going to be well, rarely will they be minimal. We almost never use minimal basis sets for anything in computational chemistry. But most of the time, your basis sets are going to be split valence or split valence polarized, maybe diffuse ones, depending on what you're doing. So the shading there represents both the basis sets and the level of theory that you are typically going to be working in. Okay, a little bit about electron correlation. I don't want to spend too much time in here. What you should remember is that the lower the energy, the better the answer. So notice the vertical arrow there is going from a very low energy to a very high energy. And what you should notice on there is when you do an ab initio calculation using something like Hartree-Fock, you get something called the Hartree-Fock energy. And that's the number, the energy value that you get out of the server. If moving down, a lower energy, meaning a better answer, if I were to have an infinitely good basis set, eventually I would reach what's called the Hartree-Fock limit. Okay, using a Hartree-Fock method and the best basis set I could possibly start with, I would reach a limit, and we call that the Hartree-Fock limit. If moving down the next level, if I am able to have a infinitely good basis set and I'm able to have a pretty good mathematical method that looks at electron correlation, I'll be able to get a value called a configuration interaction, or CI, energy value, and that's even better. Again, moving down, I can get an exact solution of what we call the non-relativistic, and those of you who have taken advanced physics will understand relativistic. So I'll be able to get an exact solution of the non-relativistic Schrodinger equation, or full CI, and that's sort of what we're looking at here on the very bottom right-hand corner is the exact solution of the non-relativistic Schrodinger equation, or full CI. And at the very bottom there, I left out the E on energy, but at the very bottom there, if I apply what are known as relativistic mathematical methods, I can get almost exactly a perfect answer for what my energy is. Depending on what you're doing as you get more advanced in computational chemistry, you'll certainly be using some CI methods, but again, you'll be doing CI methods probably with some pretty limited basis sets. For example, you might be using a full CI method with a split valence or a split valence polarized basis set, and you'll get a pretty good answer, but it's highly unlikely, unless you have an extremely large computer, that you're going to be using full CI with a very advanced basis set. Okay, so that's a little bit about electron correlation. Let's talk about what's known as double zeta basis sets. So for example, if I look at carbon here, we've got a 1s2, 2s2, 2p2 electron configuration. And the wave function is dependent on something called a zeta value, which is why we call it a double zeta. And the zeta values are obtained from the basis set exchange form that you've been looking at. So what I'm looking at here, if you notice here, if I want to calculate the wave function for carbon, I'm going to look at that circle with a I in between there is a lowercase psi, lowercase wave function. So I'm looking at the contribution from the wave function on the 1s orbital. I'm looking at the contribution from the wave function on the 2s orbital, and the contribution of the wave function on the 2p orbital. And each one of these is multiplied by a contraction coefficient, which is some multiplier that tells me how much each one of those contributes. We also, of course, you should understand by now that the wave function is also dependent on the radius. You've seen that when you programmed the GTO calculation and the STO calculation, they were functions of radius. So you should know by now that the wave function does depend on where the electron is in relation to the nucleus. Okay, in a double zeta, what we're going to do is we're going to use two Slater orbitals instead of one, hence the name double zeta. Okay, so there's going to be a d value which determines the amount of contribution of the second orbital. So let's show you what this looks like here. So, and again, you've sort of got to do a little algebra here. What I've done here is I'm showing you the little wave function, lowercase psi, for the 2s orbital. Notice that it's a function of r. So if you go up, if you look up at the big wave function, psi of carbon, what I'm showing you is just the wave function in the middle there. So you should be able to, your eyes should be able to take you from the lowercase psi 2s down to the equation here at the bottom. So I'm doing an algebraic substitution here. So what I do here is I have to simulate or to mathematically represent the 2s orbital there, I have two zeta values. I have zeta 1 and zeta 2. And so I'm using the Slater type orbital twice, once for zeta 1 and once for zeta 2. And then there's a new constant in there called D, which is also found in the basis set order form. So what I need to do algebraically here is I need to take that entire mess on the right-hand side of the bottom equation and substitute that in the equation above where you see little psi 2s. And that whole mess gets multiplied by the contraction coefficient C2. Okay, this will now bring us to what's called a split valence basis set. And you've seen this before. For example, a classic example is 321G. It's actually better pronounced as 321G, but we call it 321G. So what we're going to do here, and the reason it's called split valence is because there are two types of electrons. There are core electrons and there are valence electrons. The core electrons are, of course, the ones on the inside of the atom or the inside of the molecule. Sometimes we call those inner shell electrons or inner shell orbitals, and they don't contribute very much to the behavior or the energy of the atom or the molecule. But then we have valence electrons. These are the ones on the outside of the shell or the outside of the atom or the outside of the molecule. And these are the ones that are actively participating in reactions and the behavior of the atom or molecule. So what we're going to do is we're going to treat these electrons differently. The ones on the core electrons on the inside, we're going to treat them pretty basically. We're just going to apply Gaussian GTO functions to those inner shell or inner core electrons. And the ones that are on the outside, the valence electrons, we're going to treat them a little bit more mathematically, in a more mathematically sophisticated way. So the first number you see there, the 3, means that I'm using an STO3G approximation for any electron that's in the core. Okay, so I'm using 3 Gaussian functions to approximate the Slater type orbital for all of the inner core electrons. Now, for the valence electrons, I'm going to use now a double zeta configuration. So I'm going to have two zeta values. I'm going to have a zeta value 1, a zeta value 2, and then that constant D. So what I'm doing here, the 2 there says I'm going to use a double zeta to approximate some of the valence electrons, okay? And then I'm going to, the 1 there says I'm going to also approximate the valence electrons with a single Gaussian function, okay, a single GTO. So this gets very complicated very quickly. So I'm using here a double zeta that I'm using a double zeta there. The 2 there represents, I'm using 2 double zeta functions to represent part of the valence electrons and 1 Gaussian function to represent the others. So we calculate the double zeta for valence electron orbitals or valence electrons only. And the inner electrons, again, as I said, are calculated using just an STO, GTO orbital calculation. Okay, so let's take a look at what these numbers are here. So this is a 321G basis set. So what you should notice there, you should see a 321. Under the 3 there, you see starting with the 172, the 25, and the 5. Those are the alpha values for the STO3G calculation that you're doing on the inner, the core electrons on the inside. The 0.617, 0.358, 0.707 are, of course, your contraction coefficients for this, and those should be numbers that you're familiar with there. Underneath there, where you see SP, 2, and 1, you're looking at a number 3.664 and 0.770. Okay, what you're seeing there is the 3.66 is the zeta 1 value, the 0.77 is the zeta 2 value. Okay, the minus 0.395 is your contraction coefficient for the zeta 1, the 1.21 is the contraction coefficient for the 0.77, and then the 0.23 and the 0.86 are your D values for the double zeta. Okay, so now you have three sets of numbers. Under SP110, the 0.19 number, that's your zeta value for a single Slater type orbital calculation. The 1 is your contraction coefficient. Notice that it's a 1, so it's 100%. And the 1 is your D value, and again, that comes up to 100%. So what you've got to be able to do, and this is nasty, okay, is you need to think about, and what I'm trying to show you here is how all these numbers play out. So again, looking at this, you've got your alpha values, alpha value for the 1s, you got your D values for the 1s, and the D values here are the same as the contraction coefficients. You got your alpha 2s, you got your D2s, you got your D2s and your alphas. So this is how these numbers play out. And we're not going to make you do this by hand because that would be just too mean. Okay, this is your data representation. But what you then be able to do, and you really should probably walk through this and see if you can't figure out how these numbers fit in here. So what I've done here is I've substituted in the contraction coefficients, or the D values you see there, the 0.6176 number. I've substituted in the zeta values, for example, the 172 number there. Excuse me, I've tried to substitute those in. So it's not a bad exercise to try to go through and see if you can figure out how these numbers get substituted in there. So here's the calculation of the 1s orbital, here's the calculation of the 2s orbital, and here's the calculation of the 2p orbital. And again, all of this is for carbon. And what you should notice there is I'm adding all these all up. So these are just simply summations. So it would not be a bad exercise to go back and try to see, can you substitute these numbers in here? By the way, GF there stands for Gaussian function, so I'm actually using the GTO approximation here to do this. Okay, you should maybe think about trying to go in and substitute these numbers in and see if you can build these functions on your own. Okay, so these are, again, the good news is that when you select a 321G basis set, that this is the mathematics that's happening. But again, you really want to have in your head a little bit about what's happening here mathematically. Okay, so if you were to have a 631G calculation, for example, you would be using an STO6G to approximate the inner electrons or the core electrons. You would be using a triple valence approximation for the valence one, so you would have 3 zeta values, zeta 1, zeta 2, zeta 3, and then you would have a single Slater type orbital also approximating the valence electrons. Okay, so there's again calculation of the 2p orbital. All right, a little bit about polarized beta sets here. What we're doing here is and I'm not going to get too much into this because many of you haven't had advanced physics, we're going to add a high angular momentum piece. So polarization, what happens as the atoms are bonding, the charges are moving a little bit, okay? So they're not staying in one place. So what you're seeing at the bottom there on the graphic is what looks like probably a p orbital, and that's exactly what this is, okay? You're seeing a p orbital, and when electrons start moving around, they sort of change the shape of what these orbitals look like. So you see the note there where I'm adding a p flavor to a hydrogen atom. If you recall, hydrogen has 1 electron, so it's a 1s1 electron configuration. But that single electron that's in hydrogen is mostly s, so it's mostly in an s orbital, but there's a little bit of it that's also in a p orbital. So maybe, 1.8 of, 0.8 of the electron is in the s orbital, and zero point 0.2 of the orbital, or 20% of the electron, is in the p orbital. So we say that adds a little bit of p flavor to a hydrogen atom. So if it's polarized, that means we're acknowledging the fact that these electrons aren't completely 100% in an orbital, like an s orbital or a p orbital. If an electron is a p electron, maybe a little bit of that p electron is actually in a d orbital somewhere. So we call this polarized. And we indicate these with an asterisk. Sometimes we'll indicate them. So you'll see 631G star there. That means it's a polarized data set. Sometimes you'll see this represented on the server. It's represented as 631G P or 631G P comma D. If you see the P comma D, that means the electrons that should be S have a little bit of a P flavor. The electrons that should be P have a little bit of a D flavor. So that's called polarized. Okay. So, and again, we double asterisk there. We would say those add P and D to hydrogen. So unfortunately, you're going to see 631G double star or 631G parentheses P comma D. And both of those mean the same thing. So get used to that a little bit. Yeah, there you go. I'm showing the alternative notation there. So if it's a single star, it's going to be 631GD. If it's double polarized, it would be 631GD comma P. So again, any S electron has a little bit of a P flavor. Any P electron has a little bit of a D flavor. You're going to see that notation. All right, diffuse basis sets. We use these mostly for anions charged. So something like Na plus, excuse me, or Cl minus, any anion, something that has a negative charge on it, not Na, excuse me, or atoms that are in the excited state. And what you see here, the graph at the bottom probably explains this the best. Here we are calculating a Slater type orbital, so we're calculating a wave function, and you notice that the value of the energy is very high as the electron is close to the nucleus. As it gets farther and farther away from the nucleus, the energy gets lower. And to save computing time, we basically cut off the tail there. You see that red line at the bottom there? Basically, once we get to a certain threshold or certain value, we stop computing because the rest of the calculation doesn't help us very much and it just wastes computing time. So we cut that tail off. In a diffuse basis set, so most basis sets ignore everything to the right of that red line there. And what we're doing with diffuse basis sets is we're adding in the tail on the right-hand side. And we're doing this because we don't want to lose any numbers. We don't want to lose any precision when we're talking about anions or atoms in the excited state, because many of the most interesting parts of anions or atoms in the excited state actually happens in that little tail section of the basis set. So we want to make sure we capture that. And what that means, of course, for your calculation is it'll take, if you're using a diffuse basis set, that'll take significantly longer time to calculate that. And we represent a diffuse basis set by adding a plus to the nomenclature, and that's how we know it's a diffuse basis set. So if you see a star or an asterisk, you know that's a polarized basis set. If you see a plus, you know that's a diffuse basis set. So again, if you're doing anything with a charged atom or a charged molecule, anything that's an anion, like SO4, 2 minus, if you were studying the sulfate ion SO4 2 minus, you would definitely want to use the diffuse basis sets. Okay, there's also what's known as high angular momentum basis sets, and I'm not going to talk about these at all. I'll put this graphic up here. Some of you, depending on your chemistry course, may have encountered these quantum numbers N, L, M sub L, M sub S, where we look at the principal quantum number, we look at the azimuthal quantum number, L, we look at the magnetic quantum number, M, and we look at what's called the spin projection quantum number, or M sub S, and you notice there electrons can have either a minus 1/2 or a plus 1/2 spin. Some of you may have encountered that depending on your chemistry. And for the high angular momentum basis sets, we're reestablishing our basis sets based on these quantum numbers. And again, if you recall the first table that I showed you, high angular momentum basis sets are way down the list of complexity in terms of basis sets, and we don't use those very often. There's also what's known as correlation consistent or CC basis functions. And I'm not going to say much about these. These are a family of basis functions of increasing size. And we use these to try to approach the basis set limit. So we use these CC basis functions to get us as far down the left-hand side of this chart as we possibly can. And if you take a look at the basis sets, if you actually look at the numbers for these things, these are very complicated basis sets. So for example, a CCP VDZ is a double zeta basis set with D's on the heavy atoms, like carbon will have, remember carbon is 1s2, 2s2, 2p2, but we'll put d orbitals on carbons, like which are heavy atoms. Anything more than hydrogen is a heavy atom, and we'll put p's on the hydrogens. The VDZ there means valence double zeta. Okay, we might use a CPVTZ where TZ is triple zeta, 6Z is 6 zetas. We can also augment these correlation coefficient basis sets with a diffuse function, so that's equivalent to putting a plus sign in there. So what you should take away from these with these correlation consistent basis functions is we're really trying to push the chart down the left-hand side of the page. And if you're using any of these CC basis functions, we probably are going to assume that you know what you're doing at this point. And I should say that most computational chemists who are doing research are using one of these more advanced basis sets. Rarely are they using, they certainly almost would never use something that's a minimal basis set. We'll use split valence basis sets routinely for pretty basic calculations. And again, that's what you're mostly using. Occasionally we'll use polarized. Again, we'll use diffuse if we're dealing with anions or excited state chemistry. But most people doing big boy, big girl computational chemistry are using one of these correlation consistent or CC basis functions, which get us much farther down the left-hand side of this chart than you will probably be doing. Okay, if there's any questions, we'll talk about them in video conference and hope to see you online. Thanks very much.